Welcome to InfluxDays. This is an overview of the InfluxDB Time Series Engine. My name is Dean Sheehan and I'm the EMEA Field CTO here at InfluxData. In this presentation, I'm going to take a look at an introduction to the InfluxDB Time Series Engine. I'm going to describe the relationship of that engine to the API, the relationship to Flux, the relationship to tasks, and then I'm going to take a brief look at the future of the InfluxDB Time Series Engine. At the core of the InfluxDB Time Series database is the Time Structured Merge Tree, TSM. We use that term to refer to its storage format on disk and also the processing engine that takes data in, ingests it, indexes it, compacts it, and lands it on disk, as well as is responsible for supporting the queries. It's purpose-built for storing time series data. It's been battle-tested over many years by a large community of users in a multitude of situations. And it's designed to continuously ingest large volumes of new data points whilst also supporting real-time queries. The InfluxDB Time Series Engine is highly performant, very fast. Here's some examples of some ingestion figures, some performance figures for InfluxDB based on different cardinalities and the version of that engine over time. So we've made continuous improvements in the time series engine. We've also made some significant changes between an in-memory index and what's called the TSI1 disk format index. And so right now, if you looked at the situation on an Amazon EC2 machine, an M4 2X large, if you're looking at a million different kind of series of data in your data set, then we're capable of recording right now about 188,000 new values per second landing against those 1 million kind of data series. The InfluxDB Time Series Engine isn't really sensitive to how much data you have on disk. We don't care whether or not it's 1 gigabyte, 100 gigabytes, 100 terabytes or petabytes. So we're really not sensitive to the data volume. However, we are a little bit sensitive to the cardinality, just how many series you have that are being handled by the engine. But we'll talk more about that a bit later on. The time structured merge tree, it draws on previous work from others called the LSM, log structured merge tree. And that's both its structure, its format on disk, format in memory, and the algorithms. It's organized around time, series, and fields. And it's in a columnar format. The data blocks on disk go through compaction and compression stages. So when data first lands in Influx, we hold it in quite a sparse format that's readily easy to write new data to. So we can ingest data at high performance, landing that data onto disk in a way that's indexed and is queryable. But that isn't actually the best for disk use. So over time, as we established that actually data blocks are less likely to be written to add in new data, then we put them through compression algorithms and compaction processes to reduce the space they use on disk. The columnar format for data is very compression friendly. If you imagine a temperature sensor and the value of a temperature sensor changing over time, then it might make very minor changes between hour to hour, day to day. And so things like delta compression can be used to just record the increments between one day and the next, or one measurement and the next. This is very different from data structures that are more row oriented, where actually adjacent on disk would be not only the value of the actual temperature value, but maybe the air pressure, the electrical voltage, and having those things arranged contiguously on disk means that actually compression can't be as efficient. So in a columnar format, highly amenable to compression, and actually the compression algorithms we use are very dynamic, and they'll change over time based on heuristics and what we see in terms of the shape of the data that's landing. The time structure merge tree is a proprietary format when sitting on disk. If we look at the API inside the InfluxDB Time Series Engine, then it's one API to rule them all. So InfluxDB has a variety of deployment methodologies and approaches, be it our open source single node community version, be it the multi-node enterprise self-managed cluster, or be it our cloud service. It's one API. And that API covers receiving or ingesting new data in the line protocol format, executing queries in one of two query languages, InfluxQL and Flux, and processing that in the background that goes on and is expressed by the Flux tasks and the Flux language. It's one API all sitting on top of the time series engine and really hiding the details of that time series engine. So you don't need to worry about what index format, what version of the time series engine is being used. That API is stable. And the fact that the API is not only stable and hides the implementation details of TSM, and it's also consistent between open source, enterprise, and our self-managed kind of and the cloud service. The fact that it's actually consistent between all of those means that you don't have to worry about it, and it means that actually you can choose to move. So it might be that actually you start on our cloud service, delivering your solution to your customers, and then you might have customers that actually need, for reasons, maybe regulatory reasons, even technical reasons, they can't be using a cloud service. Then actually you can deploy our Influx Enterprise to support them in that particular situation, and your application doesn't have to change. It's all still using the one API to rule them all. Similarly, we have customers that actually start off building solutions as startups on single board computers using our open source, and then they have a view in time that actually they're going to get to the point where they're actually kind of aggregating data between many different Raspberry Pis, for example, and aggregating all that data in the cloud. The API doesn't change. So you can move in either direction, and as well as moving, you can even blend, have multiple solutions, and possibly even synchronizing from the edge to cloud, all up to you, all using the same API, and that one API hiding the implementation details of the time series engine. So once again, the API of InfluxDB at the front, on the left-hand side of this diagram, is about ingest, and it's about taking data from a variety of different sources. We really don't, we're kind of data source agnostic, if you will, bringing that data in, moving that data through the ingestion process into the buckets into the center. Those buckets in the center of that diagram represent the storage on disk, and that's really where the time structured merge tree is at the fore, the structure on disk. The API for managing that data, the management of that data might be about setting retention policies, creating new buckets, deleting or moving or copying existing buckets. And then on the right-hand side, actually leveraging that data, and that can range from kind of at the top aspects of query through the InfluxQL query language or through Flux. And then maybe as you move kind of down towards the bottom, automation, where that data is being looked at periodically to see whether or not there are anomalies, whether or not data should be downsampled, whether or not new data and KPIs should be derived, and whether or not external automations and triggers should be enacted. All accessible through the API, all sitting on top of the time structured merge tree. So our Flux language, we often call it a query language, but it's more than just a query language. It's a functional data manipulation language. It's functional in style. It allows you to actually request data out of Influx in ways you might consider to be querying, but also then to transform that data, put it through a lot of manipulations, including things like conditionals, maps, iterators, various things like that, and then actually perform actions such as performing a post or sending out a data to an external handler like PagerDuty. It's very flexible, it's very powerful. It is actually surprisingly easy to write once you've actually got your head around it just a little bit, and it is actually very easy to read. The Flux language and the TSM engine supports a concept called pushdowns, and this is a mechanism by which the query, the Flux execution engine, is looking at the Flux script that it's been presented with, and it works out which aspects of that script can actually be pushed down very, very close to storage. So, for example, filter operations get pushed right the way down to the storage level, so that actually we are kind of retrieving less data off disk. And then the remainder of the Flux script will perform the higher level kind of filtering, aggregation operations, etc. So pushdowns are a very powerful concept in the TSM engine. So, but just Flux is not just there just for querying data. It also allows you to express background processes that should be running without a user in front of them to do all manner of things, once again, such as alerting or downsampling. So that takes us to tasks, Flux tasks, your heavy lifting friend. So in the background, you can take Flux, represent it as a Flux tasks, give it a schedule, and tell it that, for example, every 1 second or every 1 hour, take a look at some new data that's kind of come in from all of your devices, from the servers you're monitoring, or the solar farm, wherever that data comes from. Take a look at that data that's landed on disk in the time structure kind of merge tree kind of system format. Take a look at it and maybe downsample it, turn it into daily averages, and write those daily averages back to another part of the system, another database or another bucket within Influx, to support possibly even much faster queries, much faster kind of user experience in navigating that data. But also, should you want to, just reducing the data size if you know that actually the raw data is very important to you when it's maybe 6 months old. So that's downsampling. Also, pre-computing and downsampling are very, very similar. Downsampling, we would say, is actually really just reducing down the data through statistical mechanisms, looking at averages and recording, once again, those hourly averages, for example. But also pre-computing, maybe actually taking power and voltage and turning that into energy or something like that. Whatever kind of derived mathematical operations you might want to perform. So maybe calculating those derived metrics and storing the derived metric alongside your raw data, once again, to support an easier kind of user experience when it comes to navigating that data. Flux tasks can also look at that data and look for abnormal kind of situations in the data. You might call them events, alerts. You might call them anomalies, anomaly detection. But these are processes that are going on, described in the Flux task language. They're being executed in the background. They're looking at your data and making decisions about what to do with it, downsampling it, pre-computing with it, and maybe actually determining that there's something about this data that requires some external automation or maybe some user interaction to go look at the data and decide that actually, yes, it is an anomaly and we need to go and fix the turbine, for example. If we now take a brief look at the future of the time series engine, we're making some changes. We want to make the format of the data on disk as open as possible, and so the time structure merge tree is a proprietary format, but we're moving to Apache Parquet, and so the Parquet format now become kind of the de facto standard for Columnar data on disk, and that will be available in object storage, so making it much more accessible to other processes without pulling it back through our API. We're always looking to improve speed. Speed is paramount when it comes to databases, and we're making use of the Apache Arrow work, which is an open source standardized columnar format for data in memory. And once again, that's been worked on by the community, highly optimized for columnar data in memory, and is used by the new time series engine to interchange data between different parts of the system. We also want to make sure that we're open and accessible to people with different experiences. So we have our InfluxQL query language that's been with us from the start, and we have maybe 500,000 databases right now with people writing queries in InfluxQL. Our Flux query language, our Flux data kind of transformation language, is very powerful, very extensible, and we continue to kind of drive that forward. And we believe that if you have no other experience, no other things driving your particular needs, that Flux is a great language to express the work you need to do over time series data. But we also appreciate that actually there is a body of people out there, and more than people, tools out there that are fixed with respect to SQL and things like the Postgres wire format for expressing or for communicating kind of SQL. So we're actually going to be expanding the time series engine to support SQL natively. Going back to my very early slide where I said that the time series, the time structured merge tree, didn't particularly worry about how much data you had on disk, but was maybe a little bit sensitive to how many different time series you had, cardinality in other words, and it was kind of sensitive to that. Right now we're looking to unlock seriously or ludicrous kind of cardinality, and for no longer cardinality be something that you should be concerned about. So if we look actually at the structure of the new time series engine that's called, that's being powered by the project we called IOX, then data comes in through our API tier, lands in a durable queue in Kafka, and then goes through what we call the ingester processes, which are using that arrow, columnar in-memory data format, and they are ingesting the data into that format, looking at it, creating various indexes and things, and turning it into Parquet files that are stored on the object store. We then have queries that come in through the query engine, and those query engines are, once again, they're native in terms of SQL. That's the lowest level kind of language we're supporting, but on top of that, we will be continuing to support Flux and InfluxQL. Okay. And then there's the compactor that's looking at the Parquet files on disk, and at the right time is reducing them down in size, making sure that actually we're doing our best to minimize the storage requirements on disk for data. That brings us to the end of this presentation, and here's some additional resources that I want to bring to your attention. We have our open source or cloud, very easy to get engaged with InfluxDB without any kind of commercial contracts, or without even having to stand up any infrastructure in the case of cloud. We have our forums, we have Slack, we have our Reddit, the Influx kind of GitHub community. There's a great book from us called the awesome InfluxData.com, our documentation, our blogs. InfluxDB University is a great new asset out there to allow you to start your journey with understanding how to use Influx. And then our documentation, which contains a variety of how-to guides. Thank you very much.